Okay, so I'm redoing the nodal analysis lecture because I recorded the entire thing without the microphone on. So I might cry during this video, but we'll get through it. So we're going to start talking about streamlined circuit analysis techniques. So brute force was taking a whole bunch of equations, taking everything we could learn about a circuit and kind of throwing it together into one big set of equations. And so we called that brute force because it was a lot of work to get to where we needed to be. We learned some tools. We learned things, how to simplify, how to expand back out. We learned how to deal with voltage division, current division, simplify equations, simplify like elements, that sort of thing. And so now we're kind of ready to move into something that's a little bit more higher level circuit analysis. And these are more streamlined techniques. The first two techniques we're going to talk about that are part of this module 4A are nodal analysis and mesh analysis. Now, these are techniques where we're going to solve for a set of variables, and using those variables, we can solve for every other voltage and current in the circuit. Okay, the other two circuit analysis techniques, which I've put into module 4B, are ones where we typically solve for a single voltage or current in the circuit. So knowing using that technique doesn't allow us to solve for everything. Okay, so we're going to start with nodal analysis. So nodal analysis. And nodal analysis is simply a streamlined version of KCL, of Kirchhoff's current law. Okay, we are going to write KCL equations. We're still going to write them. In terms of a new type of variable we haven't used before, in terms of node voltage variables. Okay, we're going to call these KCL equations, we're going to call these now nodal equations. All right, now at the end of the day, we are still summing currents. That's what KCL is, right? We are summing currents. All right, so let's talk about the hierarchy of writing down currents before we talk about the steps for nodal analysis. So hierarchy for writing currents for our KCL or our nodal equations. All right. We're going to basically do a set of steps here. So we're going to say at the top of the hierarchy is one item, and then we're going to step down through that hierarchy. All right. So there are only three ways we can write down a current in this class. Okay, at the top of the hierarchy, and perhaps the easiest one, is do we see a current source? Because if we see a current source, it doesn't matter what else is with that current source. It could be in series with a million resistors. The current is still that current source. Okay, so we know what the value is. The current is just the value of the source. All right. 2, if it's not a current source, is there a resistor? Because if it is, we know that I is equal to the voltage across that resistor divided by the resistance itself. So it's very easy to find the current through a resistor. So if it's not 1 and it's not 2, we only have one more option. And that option is to label a current variable with a direction. Okay, those are our three choices. We can't do anything else other than that. Okay, so let's talk about the steps for nodal analysis. All right, step 1. we are going to identify all nodes with 3 or more connections. Okay, so we're going to look at the circuit, and any node that has 3 or more connections, we are going to take note of. Okay, we'll darken it in with a little circle like we've been doing for brute force. Then step 2, as we consider all of those, and we're going to have at least 2 in any circuit that we are going to solve using nodal analysis. We're going to have at least 2 nodes with 3 or more connections. All right, so for those nodes, we are going to choose one. So choose one node from part 1, or from step 1, let's say. To be the reference node. Okay, so all of our other voltages in the circuit are going to be relative to that reference node. Okay, and so the reference node, and we're going to ground that reference node. Okay, and ground simply means assigning 0 volts. Okay, now we don't just say it's 0 volts. What we do is we put a circuit symbol in. So, and there are 2 circuit symbols we can use for ground. So if we're grounding this node, for example, here, okay, it has 3 connections. We can use a series of decreasing in length parallel lines, or we can use a arrow like this. Either one of those is acceptable for a ground circuit symbol. Okay, so once we're going to choose one of those reference nodes for grounding. We will talk as we work examples about which reference node should be grounded. It doesn't matter in the grand scheme of things. So just like we did in brute force, it really doesn't matter which way you label voltages and currents. Same thing is going to be true here. It doesn't matter which node we choose to be the reference node. As we work examples, I'll give you tips on how you can choose a reference node to make the math less tedious. Okay, the math after you write your equations down, a little less tedious, but it really does not matter which node you choose for the reference node. And we'll see that as we move along. So step 3, for whatever nodes we have left, and we'll have at least 1 left, so we're going to label each remaining node from part 1. With a node voltage variable. Okay, so remember that was our, pulling up here to the top page, we're going to write KCL equations in terms of node voltage variables. So we're going to label them here in step 3. So any node, after we choose our reference node, any leftover node with 3 or more connections is going to get a node voltage variable. And you're going to label them with a subscript that makes sense. So I typically use V1, V2, V3. You could use VA, VB, VC, VX, VY. It doesn't really matter, okay? But we're going to give them that variable, and those are things that we're going to solve for eventually. All right, so step 4. We are going to write our nodal equations, which again are just KCL equations. So we are going to write nodal equations at each node from part 3, or from step 3. Okay, so we're going to write a nodal equation for each node. All right, and we're just writing a KCL equation. All right. And what we're going to do differently than we did for brute force here, I like to use the version of KCL where we sum the currents leaving the node. Let me write that differently. We're going to sum currents leaving the node. Okay, you don't have to do it this way, but this is the way I'm going to work the problems in class. I think this is the easiest way to do it. So that's our KCL version. We're going to sum the currents leaving the node. Then step 5, we will write any additional equations, and most of the time we won't have any additional equations, but we might write any additional equations as appropriate. Then we will simplify all of our expressions and solve. And we'll solve for our node voltage node voltage variables, and then we will solve for whatever other currents and voltages we need to solve for. We can, in fact, solve for everything based on the node voltage variables. Okay, so we can do just like we did for brute force. We can solve for every other current and voltage, and we can solve for power associated with each element. So these are the steps. We're going to follow them every time. We are never going to vary from these steps. All right, so we're going to start with a very simple circuit as an example. So we have a 5-volt source. We have a 4 ohm resistor. We have a 1 ohm resistor. And we have a 2 amp current source. So 2 amps, 1 ohm, 4 ohms, and 5 volts. Okay, hold on just 1 second. Okay, so we have to, so remember the steps. We identify nodes with 3 or more connections. I'm going to do that little node mapping thing with the highlighter pen here. So we have a node down here where we have 3 or more connections. We have a node up here where we have 3 or more connections. So there's just 2. We have a node here, but it only has 2 connections, and so we don't care about that node for nodal analysis, so we're going to leave it alone. All right, and I'm going to demark it with a blue circle here, a blue dot for each one of these. Okay, so we've identified our nodes with 3 or more connections. Now we need to choose one of these to be the reference node. Most of the time for these sort of rectangular circuits that kind of look like ladders turned on their sides, I choose the bottom node to be the reference node. That way my currents, I'm summing the currents leaving the node, they're all flowing towards the bottom, towards ground. But it does not matter, but this is the way I'm going to do this one. So I've chosen a reference node, and now I'm going to label the other node with a node voltage variable V1. So the next step is to write KCL equations. All right, and so we are going to solve or express currents equation, terms in our KCL equation, our nodal equation for currents leaving the node. And I've drawn these in red. I'm not going to do this every time. Okay, but as we get started, I like to have some landmarks for you. So we are going to express each one of these currents, the current flowing to the left, the current flowing down, and the current flowing to the right. Those are our 3 currents leaving the node. We can sum those expressions into one equation to 0, and we'll have our KCL equation or our nodal equation. So let's start with the current flowing to the right. So the current flowing to the right is this current. Okay, it flows through that current source. All right, remember the hierarchy. Is there a current source? If there's a current source, we know what the current is. Okay, except that this current flows in this direction and the source flows in the opposite direction. So for our nodal equation, I'm just going to call it node 1, the current flowing to the right is going to be -2 because it's opposite to the way the current source is flowing. Okay, plus the current flowing down. So the current flowing down, this current here, okay, it's a resistor. So we know that we need the voltage drop across the resistor, and we divide it by the resistance to get the current. So what we need, we have the resistance, right? The resistance is 1. So what we need is the voltage drop across this resistor. And here's where those node voltage variables are going to come into play. Okay, so let's talk for just a second about what we want to solve for. We want to solve for the voltage drop across this resistor. Okay, this voltage drop across this resistor. All right, the current is flowing in this direction, so we need a voltage. We need to express the voltage such that the voltage drop has that polarity, right? So the current's flowing from plus to minus, okay? And the passive sign convention will hold. Now, again, I don't like drawing in these pluses and minuses, but I'm going to do it for the first couple examples just to give you some landmarks to look at. But after that, you really need to not include these, mainly because as we get into more complicated circuits, these pluses and minuses are going to change based on which node you're analyzing. And so this can get confusing and can really muck up your circuit and make it harder to read and analyze. But we'll do it to get started. So I need the plus here. So remember the electrical body stuff we did from the first lectures. So plus V1, the voltage at that terminal, minus the voltage at this terminal or node, has to give us the voltage drop across that resistor. Okay, so this voltage here is going to be plus V1 minus the voltage here at ground, which is 0. We divide it by 1, and then we have the current. Okay, of course, the plus signs here are understood, and eventually I'm going to stop putting in those minus zeros whenever we're subtracting ground because that is also understood, but we'll keep them in here to start with. Okay, so that's the current flowing down. This one is easier because there's only a resistor between the node voltage and ground. Now, plus the current flowing to the left. So the current flowing to the left is a little more challenging because in addition to our resistor, we also have this voltage source. And both the resistance and that voltage source are going to help us determine our current. Okay, so again, we're asked to solve for the current in this direction because we're summing the currents leaving the node. Okay, and so that will imply a voltage drop with that polarity across that resistor. All right, so we need to express the voltage that way. At the plus terminal here, we know what that is. It's V1. The minus terminal, it's not as clear yet. So what we need to do is eventually we need to find the voltage at this node here relative to ground. Okay, so I'm going to call this Vx, and I'm going to do a little aside over here. So finding Vx. So we're going to do the same sort of electrical body stuff we did the first day of class, or the first couple lectures in the module for module 1. So we're going to have plus Vx minus ground has to equal 5. We're just following the polarity of that source. So plus Vx minus 0 has to be the value of the source 5. Again, plus Vx minus 0 is equal to 5. So Vx is just equal to 5. Okay, so I'm going to put that up here too. All right, so now when we solve for this voltage or express that voltage, okay, to find the current, we know that the current is going to be the voltage drop across the 4 ohm resistor, and this voltage, again, I'm going to put in the plus minus just for now. Okay, so we're going to have plus V1 minus Vx, which is 5. So we're going to have V1 minus 5 as the voltage. We divide it by the resistor 4 to get the current. We've summed all 3 of our currents together, so we can sum that to 0. So now we have one equation, one unknown, And that's V1. I didn't put V1 there. I'm sorry. It should be plus V1 in that second term. So now we need to collect terms and solve for V1. V1 is our node voltage variable, and we can solve for every other voltage and every other current in the circuit once we know V1. All right, so looking at this equation and simplifying, what I like to do is I like to take the variable here, V1, and then put all of the coefficients associated with that variable. So I've got 1 over 1 from the second term plus 1 over 4 from the third term, and this has to equal, I'm going to move everything else over to the right-hand side. So I'm going to move 2 over and plus 5 over 4. And then I can start to collect and simplify here. So I've got V1 times 1.25 is equal to 2 plus 1.25. So that's 3.25. And so when I solve for V1, I'll get that V1 is equal to 2.6 volts. Okay, so that is my voltage, node voltage for this particular circuit. Okay, so how do I use this to solve for every other voltage and current in the circuit? Well, if we look here, we have all three currents that flow in this circuit expressed in our node voltage equation. Now they're expressed such that they're flowing in this direction, and this direction. So we don't have as much control over the directions of the current, but that's okay. All right, so what we're going to do is we're going to solve for every voltage and current in the circuit and then solve for power. All right, this is going to be different because we're not going to label variables for every voltage and every current in the circuit. We're more concerned about power at the end of the day. Okay, so this may be a little bit of a struggle, so you might have to start and stop this again. Okay, so let's talk about first the 2 amp source. There we go. 2 amp source. Okay, so for the 2 amp source, we have to find the voltage drop across this source. Okay, and how we solve for it is up to us. What reference we give it is up to us. I want to solve for it so that this is the positive and this is the negative of that voltage Vs. I'm going to call it Vs just for purposes of this little diagram here. This is going to disappear, of course, because it's the highlighter or the laser pointer. All right, but I want it that way. Why? Because I want the current to flow from minus to plus so that I can solve for power delivered. So what is that voltage going to be? That voltage is going to be plus, I don't want that. I switched to highlighter too fast. Plus V1 minus ground. Okay, so the voltage is going to be plus V1 minus 0, or 2.6 volts. With the polarity that I wanted. I haven't labeled a variable yet. Okay, and I don't need to because what I'm really solving for here is power. All right, so P is equal to the voltage, 2.6, times the current, value of the source, 2. So this is going to be 5.2 watts. Okay, so 5.2 watts, the way we expressed this voltage to find the power, we expressed it or referenced it such that the current was flowing from minus to plus. So this power is delivered. Let's do the other source, 5 volts. Okay, we know the value of the voltage. We just need, or the value of the source is the voltage. We need the current. The current is sitting in our nodal equation. It is right here. Okay, but it's this current flowing in this direction, which is going to give us power absorbed. We have to just recognize that and change it later. Okay, so 5, the current through the 5 volt source, I'm just going to call it I here, is equal to that node voltage equation, V1 minus 5 over 4. I'm not labeling a variable. I'm just kind of abstractly considering the current through that source. All right, and so that current is equal to Please hold. I have that written down for some reason. So that's minus 0.6 amps. Okay, and remember that that current is this current here, the current that flows from plus to minus through the source. So now when we solve for power, P is equal to V times I, so V is 5, I is minus 0.6, and this is going to be minus 3 watts. But this power is absorbed because the way we solve for the current using the expression from our node voltage equation solves the current in this direction, so that gives us power absorbed. All right, and so we're going to change this around and say P is equal to plus 3 watts delivered. And so the sum of the power delivered is equal to 5.2 plus 3, or 8.2 watts. All right, let's do the resistors. So 2 resistors. I'm going to start with the 1 ohm resistor. So for resistors in nodal analysis, by the way, since we're solving for node voltage equations, I always say it's better to, or I always say, what I typically do is I use for resistors, P is equal to V squared over R. All right, so we know that the current for each resistor is sitting here, but we don't really need to solve for that unless we're asked to. Since we're solving for power, I'm going to go with V squared over R. So I'm going to start with the 1 ohm resistor. We know the voltage drop across the 1 ohm resistor is plus V minus 0. Okay, we did that right here. It's sitting in our nodal equation. That's the voltage drop across the 1 ohm resistor. So we can write that power is equal to V1 squared over R, which is 2.6 squared over 1, which is equal to 6.76 watts. And of course, it's absorbed. Okay. Then the 4 ohm resistor, P is equal to V squared over R. V, what is V? It is sitting right here in our nodal equation. This is the value of the voltage across that 4 ohm resistor. Okay, I find, and just let me stop here for a second, I find oftentimes that students struggle at this point to find the voltage drop across the resistors when they go back to solve for power. It is sitting right here. You've done the work already, so use that, V1 minus 5. So the voltage is V1 minus 5. We'll square that, divide it by the resistance here, which is 4. So when we substitute V1 into that expression, we'll get that this power is 1.44 watts, and we know it's absorbed because resistors can only absorb power. And so the sum of the power absorbed is equal to 6.76 plus 1.44, which is equal to 8.2 watts, which makes us very happy because our power delivered is equal to our power absorbed. Okay. Let's work a little bit less trivial of a problem. What happens if you have more than just one node voltage variable? Okay, here we had 1, so this was pretty simple. What happens if you have 2? And I'm going to move to a new page to do this. Okay, so we have a 10 volt source with that polarity, a 12 ohm resistor, a 3 amp source, a 10 amp source, a 4 ohm resistor, a 6 ohm resistor, and a 2-volt source. Okay, we're going to solve for the node voltage variables, and then we'll solve for the power delivered by each source and absorbed by each resistor. Okay, and then I think the next example after that, we'll start solving for something very specific in the circuit. So this will be the last time we solve for power delivered and absorbed for each element. Okay, so we identify the nodes with 3 or more connections. Okay, I'm going to use the highlighter again for this one down here. We have all of these connected down here at the bottom node. So there's a node there. There's also a node up here where these 3 come together, and there's a node here where these 3 come together. There is a node here, and there is a node here, but it only has 2 connections each, and so we're not going to use those. So I'm going to call this node voltage variable here V1 and call this one V2. Does it matter which order you go in? Absolutely not. You could put V1 on the right and V2 on the left. Okay. So we've labeled our, and I didn't say this at first. Let me go back here. I'm going to ground this bottom node, which I didn't do. And then I'm going to call this node, the top node V1, to the left, and the right one V2. I chose this node as my reference node because, again, it's at the bottom, and it also has the largest number of connections to it. Okay, so from a mathematical standpoint, it's better to choose that as your reference node because you have fewer terms in your equations. But again, it does not matter. I could have chosen any one of those nodes to be the reference node. Okay, once again, I'm going to sum the currents leaving the node, and this will be the last time I label these. And I'll tell you, and you'll see why here in just a minute, why labeling these currents can be problematic. Okay, and we're going to try to do this without labeling voltage polarities as well. All right, so we want to start with node 1. We analyze each node independently. So once we analyze one node and write its nodal equation, we forget about it and we go on to the next node. Okay, so node 1. Let's start with the current flowing down. It doesn't matter which current we solve for first. The current flowing down is nice and easy. It's this current here. The source defines it. So we have plus 10. Okay, plus the current flowing to the left. Okay, we want this current here. So this is our voltage drop across that 4 ohm resistor that we want based on this current. Okay, this voltage here is going to be 2 volts relative to ground, just like we did last time. So I'm just going to label that in here. Let me do it in a different color. So this is still plus 2 volts there based on our electrical body stuff, just like we did for the first example. So the current flowing to the left is going to be the voltage drop plus V1 minus 2 divided by 4. Okay, so the voltage drop is V1 minus 2. We divide by 4 to get the current. Plus the current flowing to the right. Okay, we want the current now flowing in this direction. Okay, which will imply a voltage drop with that polarity. Okay. So, so we will have plus V1 minus V2 as our voltage drop. So plus V1 minus V2 over 6. So we've got our 3 terms, our 3 expressions for the current flowing in each direction, right, left, and down. For node 1, we can sum to 0. Okay, so when we have a second node like we do here, we don't treat it any differently. We just have to make sure that we're solving for the right polarity of our voltage so that the passive sign convention is holding. So the current is flowing from plus to minus, so plus V1 minus V2. Okay, now that we've written node 1, we forget about it and we move on to node 2. Okay, node 2. Again, let's start with the current flowing down because that's easy because there's a current source there. And we know if there's a current source there, we know what the current is. However, in this case, the current is flowing opposite to the current we want. So we will just change the sign. So it'll be minus 3 plus the current flowing to the right. Let's start with this one. So we want this current. It implies a voltage polarity such that the current's flowing from plus to minus. So it'll be plus V1 minus the voltage here. Now note the difference in this voltage source where the voltage source is flipped relative to the voltage source on this side. So what does that tell you about the voltage at this node based on the electrical body? It's going to be minus 10, right? Because you'll have plus 0 minus 10 gives you 10. Okay, so now we're going to solve for the current here. So remember, we still have we're just finding the voltage drop across the 12 ohm resistor. We'll divide it by 12 and we'll get the current. So the voltage here is plus V2 minus a minus 10. Okay, so V2 plus 10. Plus the current flowing to the left. Okay, we want this current now. We don't care about that current, the one that we solved for here. We need this current, which means we need to express the voltage with that polarity, which will be plus V2 minus V1. So this voltage here for the 6 ohm resistor is going to be V2 minus V1 over 6 is equal to 0. Okay, two equations, two unknowns, V1 and V2. Now let's look at these nodal equations and notice the pattern that exists here. Okay, when we write our nodal equations, whichever equation we are working on, we have that node voltage minus the voltage on the other side divided by the resistance when we look at the current through resistors. Okay, the current sources are obviously just the value of the sources. Okay, so keep that in mind. When we get to node 2, we see that when we're working on the current through resistors, it's the node voltage we're dealing with, node 2, minus the voltage on the other side, divided by, the resistor. All right, so two equations, two unknowns. Again, we will solve, and what I do is as I simplify, I collect terms. So I've got V1 times 1 over 4 plus 1 over 6 plus V2 times minus 1 over 6. And then I move all the constants over to the right-hand side, which in this case is going to be 2 over 4 minus 10. All right, node 2, same thing. We will have V1 times minus 1 over 6 plus V2 times 1 over 12 plus 1 over 6. And then we'll move all the constants over to the right-hand side. So that'll be 3 minus 10 over 12. And so when we simplify these two equations down, we will have please hold. Here we go. We will have V1 times minus, or excuse me, 0.417, not minus, plus V2 times minus 0.167 is equal to minus 9.5. And V1, the second equation, is going to be V1 times minus 0.167 plus V2 times 0.25 is equal to 2.167. All right, so we will do the math here, and we'll get that. And you can use any method you want. You can do row reduction, you can do Gaussian elimination, you can do Kramer's rule, you can do substitution, you can, whatever method, use your calculator, you can use MATLAB. I don't care what you do here for solving these equations. That is entirely up to you. Okay, this is something you should already be able to do. So V1 is equal to minus 26.36 volts, and V2 is equal to minus 8.94 volts. So those are the values of our two nodal equations. Okay, so now we can solve for power. All right, so I'm going to grab the circuit and pull it down so we can see it. Okay, so let's start with the sources. And we will use P is equal to V times I. Okay, so if we look at the current sources here, and we think about what the voltage drops look like across the current sources, this is V1 and this is V2, right? Plus V1 minus 0 gives us V1, plus V2 minus 0 gives us V2. Okay, so we know that. So it's easy to find the powers associated with this. Okay, so if we look at the 10 amp source, we're solving for power delivered, but the 10 amp source flows from plus to minus with respect to that voltage. No big deal. We can either solve for power absorbed and then switch it, or we could go ahead and switch it here in the equation. So P is equal to minus V1 times 10. So the minus in front of V1 shifts the polarity, so we're solving for power delivered. So V1 is equal to minus 26.36. So this will be 26.36 times 10, or this is going to be 263.63 watts, and it is delivered. Okay, delivered because we went ahead and reversed the voltage by putting a negative sign in there, such that the polarity shifted, so the current was flowing from minus to plus, and we solved for delivered power. Let's do the 3 amp source. So this was 10 amps, 3 amps. Okay, so in this case, the current's flowing from minus to plus, the way the current source is oriented. So we're just going to use V times I. In this case, it's V2 times 3. So that's 3 times V2, which is going to give us minus 26.36 watts. And that is delivered power as well. It just happens to be negative here. Yeah, okay. I was just checking on something. All right, so now let's go to 2 volts. All right, so P is equal to V times I. V is 2. What is I? Well, I is the current flowing here, which is the current right here in our nodal equation, okay? But this is going to give us power absorbed, and so we're going to have to deal with that, all right? And here I just go ahead and solve for power absorbed. So I'm going to have V1 minus 2 over 4. Okay, and this is going to give us power absorbed, which is going to be minus 14.18 watts absorbed, or plus 14.18 watts delivered. Now, if you wanted to, you could go ahead and turn this around by making it 2 minus V1 over 4. That certainly is okay. Okay, I'll leave that up to you. Either answer, either way, your technique is fine, as long as you're giving me power delivered at the end for this particular problem. Okay, and the last source is the 10 volt source. Okay, so P is equal to V times I. V is 10, the value of the source. I is the current that's sitting in our nodal equation right here. V2 plus 10 over 12, that's this current. All right, so we have V2 plus 10 over 12. Now, is this going to give us power delivered or power absorbed? Well, this current here, the current that's in our nodal equation, flows from minus to plus. So this is going to give us power delivered. So this is going to be 0.883 watts delivered. Okay. Let's go on to the resistors. We have 3 resistors. I'm going to copy that again and paste it just so we can see it, so we don't have to scroll up and down. Okay, so resistors. Again, I typically use V squared over R for power because the node voltage variables are what we solve for here. But you can solve for current for each of these if you wish. You'll get the same answer. Let's start with the 4 ohm resistor. So what is the voltage drop across the 4 ohm resistor? Again, it is sitting in our nodal equation. It is V1 minus 2. So we're going to have P is equal to V1 minus 2 squared over the resistance 4. And this is going to be 201.07 watts. Absorbed because resistors can only absorb power. Let's go to the 12 ohm resistor. P is equal to V squared over R. What is V? Well, again, it is sitting in our nodal equation. Remember, it's V2 plus 10. Sorry. Here. There we go. Sorry, I got discombobulated there. This is going to be V2 plus 12. That's the voltage drop across the 12 ohm resistor. V2 plus 10. We'll square it and we'll divide by 12 to get the current. And so this is equal to 0.094 watts absorbed. Okay, because resistors can only absorb power. Okay. So then the 6 ohm resistor. So this is the one that's going to be different than the others we've done because we actually have 2 choices, right? So if we pull back up to our nodal equations, we solved for the current through the 6 ohm resistor 2 different ways, depending on which node we were working on. So here, it's V1 minus V2, the voltage drop across the 6 ohm resistor. And for node 2, it was V2 minus V1. So which one do we use to solve for power? Which one? Any thoughts? I know you can't answer me, but think about it for just a second. Is it V1 minus V2? Or V1 or V2 minus V1? The answer is it doesn't matter because we're going to square it. And V1 minus V2 squared is the same as V2 minus V1 squared. So it does not matter which one we use. We're going to get the same answer. So I've got V1 minus V2. It's going to give us 50.58 watts, and this is absorbed. Again, we don't have to worry about which polarity we're choosing for that voltage because we're going to square it, which means we get the same answer. Okay, so those are 2 basic circuits. I'm going to work 3 or 4 more in the example part. So we'll go to those. We'll go to those next. So this is the concept lecture, and then I'll do those examples in the example part.